So welcome back, everybody. This is part two of the using supercomputers. And the goal of this obviously is to give you some familiarity with actually being able to run jobs and understand how you would want to interact with a supercomputer. And in this particular set of part two, I'm gonna talk about the high performance storage, albeit somewhat briefly. And I should mention as well that going forward, the newer supercomputer will have another different type of high performance storage. I will mention it briefly, even though it's not in the slides, simply because it will be later on down the track that this will become accessible. Then we'll actually talk about running jobs and hopefully give you a sense of how to use the material that's in running jobs in real world HPC. So thinking about how you're actually going to use it. And I feel free in that section, right, to really ask lots of questions of like, well, I want to do this. How do I go about doing this? Because this is my real world HPC application. Okay, so high performance storage. This was asked at the very beginning, and of course you may have in your laptops and computers SSD drives, so solid state drives that are quite fast, but they're tailored to individual user access. So not multi-user access, not many different users writing different tons of files at the same time. And so that is where Lustre and a few other different types of file systems come in for high performance storage. So supercomputers have this global storage. Is meant to be very fast, and the fastest global storage with the largest amount of sort of storage footprint is typically Scratch. So it's meant to be short-term storage. There's the idea of long-term storage at least at a supercomputing center is not something that really is done, because we want people to kind of process stuff, produce data products, and if they're really meant to be long-term, as in, stored for years, typically there are other ways of doing that. So we usually don't have that direct access in terms of supercomputers. The idea, of course, for these storage systems is that they're meant to be accessible through all nodes. So all computes can write to the storage, and specifically /Scratch, which we saw a brief introduction, is a temporary working area. So it's meant to be fast, temporary working. There is some of the computers at Pawsey, but not Zeus and Topaz, have like very specific local node storage. So this particular node storage is only accessible actually via the node itself. You can't even have another node access it, and they're not shared with other users even outside the job. Now, the key example of this storage that you guys will have access to in this training session, but also going forward, is Scratch. So /Scratch. It is shared all by all users. You have a quota of 1 million files, and it's really designed optimally for, and not necessarily lots of small files, but lots of moderate and large files, because the storage system for fast access to files, which are distributed across multiple hard drives, right? So the physical hard drives, the files are split across everything, is that they have essentially a metadata server. So they have servers that are running to figure out where files live and brief bits of metadata. So the LS that took a while this morning typically happens if you have a long wait time for LS, possibly because something is hitting the metadata servers and writing an enormous amount of files, reading an enormous amount of files. Some user is doing something that slows down querying the metadata servers of Lustre to tell you what's in the directory that you happen to be supposedly located in. So we have this directory, Scratch project name, username. And so that's in the environment variable MyScratch, which you've hopefully copied the course material into. And the idea is that Scratch is really not meant to keep stuff. So there's purged after 30 days. If a file is not touched after 30 days, it's removed. The idea is not to just like move data or rename files so that you can get around this. If they really need to keep it, then it should be moved from Scratch to somewhere else, like group or offsite storage. So you have to make sure that you move or delete your data before it's purged. Really important. There's no backup here, right? So if once the data is gone, it's gone. You can't ask, oh, can you undo the delete? That doesn't happen. We undo the purge. So transferring data, talking to this storage. So we actually have data mover nodes specifically designed for fast external connect. So you can actually then talk to these data mover nodes that will then allocate a job. I see Christian has raised his hand. Oh, okay. What is, yeah, 30 days of not using a file, as Alexis said. So if a file is untouched, unmodified, and is living in Scratch for 30 days, it's gone. There's an automatic purge going on all the time, kind of looking to see what old files exist and removing them to free up space, right? Because, so the idea for Scratch is shared. You can write lots of files as a user. You can have also access to lots and lots of data. So it's, if you needed to save 600 terabytes of data on Scratch, that's fine. If it's 600 data in a million files, 600 terabytes in a million files, that's also fine, but it's meant to be shortish term, right? Okay. So transferring data, because again, let's say you want to transfer 600 terabytes of data in a million files to Pawsey. You don't want to sit there and wait with FileZilla and so on. What you can do is put in requests if the data is accessible, let's say not on your laptop, but on some server that's up and running all the time and that you need to pull data from. Data mover nodes are a great way of essentially pulling data in, putting in a request saying, I want to copy something. And the data mover nodes will handle that copy, set up a connection, do parallel pulls, and then move stuff to wherever you want it to in the local storage system. You can obviously pull and push from these data mover nodes to outside resources. But also the data mover nodes are a great way of handling information. Oh, there we are. So an example of transferring data, at least at the command line. So here's one where you can use GUIs as well, like FileZilla, CyberDuck, etc. But the example here is just to do a command line SCP, so secure shell copy of some file to wherever you wanted to. So you have the HPC data mover nodes, and you can also copy a file using the data mover nodes. So it doesn't clog up access to login nodes, trying to do some transfers. And I will read it again just because it has at least blacklisted people accidentally before, is that if you are using things like CyberDuck, like Winzilla, FileZilla to transfer data from your local computer to Pawsey, if you've got the wrong password and you have auto retry, it will almost certainly cause you to be blacklisted because the program will try retrying all the time, like super quick, and eventually you'll run out of attempts and then get blocked. So you don't want that to happen. Don't enable that feature. Yep. And you have a question?
There is one question about uploading. Okay, so there's documented. So can you advise how to upload data to Scratch for analysis that is over 30 days old? It's on your computer. It's over 30 days old.
So the timestamp, I should say, is only for files that exist on Scratch. So once a file is on Scratch and is untouched on Scratch for 30 days, it is purged. Doesn't matter how old the data is actually, it's just how old it's lived on Scratch and untouched on Scratch. Oh yeah. But
so that's a technical. We have documented options in our documentation, and
yes.
There are some options that do not keep the original timestamp.
Yes.
And so
if you need that file to maintain its date, modification date, and the creation date, etc., then yes, there are options to do that. But remember as well that the 30 days is kind of hard limits. So if you're wanting to get data after 30 days and it hasn't been touched, it will be gone. You'll just have to make sure that you maintain this. And so good policy is, so where would we move file to a permanent storage? So permanent storage could be obviously your own compute resources like your laptop. Pawsey does not provide any permanent storage. That has to be provided outside of Pawsey. So possibly by the research group you're working with, they may have hard drives to save stuff to. If there's a Google Drive or Dropbox that they pay for access for storage, that could be another semi-permanent position. But the idea is that this only applies to Scratch. The purge policy is for Scratch. There's another file system that you saw briefly called /group, and that /group has a much longer purge policy in the sense that it's meant to be for the lifetime of the project. So if you need to move internally for analysis, and you can't get to that analysis right away. So let's say you produced a bunch of data on Scratch and you want to then keep it alive for 60 days because you know you won't get back to it in 60 days, then move it to /group where it can sit for a while. It can sit for the lifetime of the project. There are more strict limits on the amount that you can have access to. So Scratch, half a petabyte of data is kind of not an issue. If you wanted half a petabyte to be reserved on /group, which has got a longer purge policy, that requires requests for access to that type of allocation of storage. And in fact, there's also documentation on how to ask for managed storage as well. So hopefully that answers people's questions about the policies. And I mean, definitely. So here's an example where the backing up, right? So they have a cure copy and they're pulling from /group, courses 01, and they're trying to save some data. So here, group, as I said, has a longer policy. Now, I should preface as well, for the training purposes, the stuff will vanish after 3 days. So everything that you've got on your directories under like COU, XXX number wise, that's going to be gone soon. Right, 3 days it'll live and then it's gone. So don't put anything critical now. Wait till you actually have access as a formal account on Magnus for more permanent copies. Okay, so and as I said, I mentioned briefly, one of the reasons why you want to maybe think about not just doing an SCP command, especially if it's large amounts of data, it could be just the size of the data. So we have these data mover nodes in a copy queue, a partition that happens to exist on the cluster, the Zeus cluster. That copy queue essentially runs in background a job that will transfer data from somewhere to somewhere else. And so that's useful, especially if you have large amounts of stuff to transfer and you don't want to sit there and waiting and so on. And you have let's say, transfer it from one site that is always active to another site that's always active. So if you're moving from somewhere outside of Pawsey inwards or moving somewhere inside of Pawsey outwards, the copy queue is a very good way of copying data. And it happens to be on Zeus. So one thing is that people, if they want to try these type of copy commands, and we can go through it, if you submit a request on, let's say you log into Topaz and you submit a copy queue request that happens to be, the partition happens to be on Zeus, and then run SQ, you're like, you don't see it. So I will show an example of this, but I'll kind of show not necessarily with the copy queue, but with just queuing systems. You have to make sure you specify the cluster you're looking at. So that's a brief overview of transferring data. And it is, as I said, for the most part, it is, there's lots of documentation and lots of ways of doing it. The main thing to keep in your head is that I can do SCP command line stuff. I can use a graphical program, and I can actually log into the system and set up a bash script that says to the copy queue, I want to copy something. Maybe it takes 17 hours. So you put in a request for the copy, make sure that the bash script is set up to copy and move data somewhere else. And then it will start moving that data at some point when it's available. And typically copy queue stuff runs pretty quickly because usually the resources are available. I will pause here briefly to see if there are any other questions related to moving data that anybody has raised that we want to make sure we record and discuss. All good? Okay. Running jobs. So this is where we've briefly talked about this, right? Accessing compute nodes via the scheduler. So running jobs, right? You could technically, in some particular environment, some supercomputers, maybe log into a specific node, look, and then go to that node, and then maybe try to run on that node. But that's one that's not accepted typically, and that's also usually poor practice because you would just get access to one node, and there'd be other things running on it. You never want to do that. You want to access all compute resources by the scheduler, because the scheduler will figure out where best to place it to make use of the maximum resources and when it can run. And the scheduler and Slurm provide an interface for doing essentially multi-node compute. So if you think of a node, as Christian said, as sort of one computer, the computer is connected via fast interconnect to another computer, and then to make use of that fast interconnect, you really should be running through the scheduler and srun, because they provide all the hooks to make use of that fast interconnect. Otherwise, you might be communicating very slowly. Now, before I kind of show some requests for resources and running jobs, I'm going to just do a very quick aside. This will be discussed in more detail later on about parallel programming. There's different types of parallel programming, and the reason I mentioned it here is because it kind of impacts the resources you would try to request and how you might run a job. So there is, I'm going to highlight 3 different things because they have sort of 3 different types of parallelism. So one is OpenMP, which is open multiprocessing. And this is meant to be for shared memory. So there's thread parallelism at shared memory CPU. So if you have CPUs or cores that share the same physical memory, they can access it physically through essentially on the motherboard RAM, right, on DRAM, there you can run OpenMP parallelism. This cannot do, you wouldn't use this parallelism to span different nodes. It is essentially confined to one node, all right, because it's a shared memory type of parallelism. Across nodes, so distributed memory, where memory is physically located across a different chip. So you would actually have to go through an interconnect, an actual fiber connection from one portion of the computing resources to another. These are MPI, message passing interfaces. There are library routines. They exist for C, C++, Fortran, Python, Rust, R, etc. A couple of different languages. And this MPI process, this type of parallelism allows a communication between different computing elements. So it allows communication across essentially physical motherboards, where you actually have to go through a different interconnect and communicate information. So that's MPI. And the other one that we'll mention, because I think it will be useful for a decent number of the projects, because they will be running on GPUs, is GPU parallelism, or essentially non-CPU device offloading. So you can access GPUs via CUDA toolkits, via a variety of different things. But the idea is that I have a computing device that is not a general processing unit, a CPU. And that requires also active thought of the resources you're going to request and how you would program your program, set up your program to make use of that resource. You can't just necessarily immediately just use GPUs. You have to think about it. And so these are sort of 3 different types of parallelism. One is heterogeneous, right? So heterogeneous, the type of computing elements are different in GPU. You have GPUs and CPUs in the mix. You have MPI, where CPUs exist across different, if you will, nodes or computers, and then shared within the node. And of course, you can combine all 3. So the largest programs typically combine everything together to make use of message passing with thread parallelism with device offloading. So they combine all 3. All right, so you have hopefully in your head a brief idea of like, there's different ways of accessing the parallelism that's provided by a supercomputing system. It's also remembered that there's accessing software is not as, it isn't just clicking on launching an executable. There's different operating systems. There's also different compilers. We provide also debuggers and profilers to examine code and figure out if there's errors in the code or how to improve the code. There are performed mathematical libraries that exist on our supercomputers, and in general, all supercomputers, that are optimized to make use of hardware and do specific types of computation. So MKL, LAPACK, PNC, these are math libraries, typically dealing with matrices and multiplications and calculating determinants. Parallel programming libraries, MPI and CUDA. And we even also have parallel IO formats. So HDF5 is an example of a library that allows you to write in parallel. So a bunch of CPUs writing to the same file in parallel fast. Not all of the software is visible as you log in. And so how do you access this software? Well, you do it through modules. So the module system is a way of loading and unloading access to software. And you can see these set of commands. So I've got module avail, module list, module load. I'll go to the terminal to show you examples of what we would see on Zeus and Topaz, because there are differences between the 2 systems. Remember, Topaz is meant to be a GPU-oriented system, and Zeus is essentially only CPUs. So the modules that might be available will be different for the 2. And these commands are quite useful, so I suggest we give them a try. Okay, so I'm on Zeus here, and I happen to be, I'm going to do Topaz. So I'm going to do an explicit thing. This is something Kristen mentioned, which was to set up an SSH key. I had already set this up. I'm happy to show this later on. It might speed up processes as you do stuff. Okay, so I've got two terminals set up just to kind of highlight things. I'm going to go to home. So if I do a module, let me bring this to the top of the screen. So module, the module command, we can even do man, well, I'll do modules because it'll be simple. Module avail. This command shows you the modules that are available. So you'll see suddenly this output of a list of names, essentially of software or libraries. You can see things that you might recognize if people are familiar with Python. There's a module that's called NumPy, and that is to provide access to the NumPy library. So here as well on Topaz, there is, for people who are somewhat familiar, but I'll just mention here, CUDA, and these CUDA modules are essentially NVIDIA library modules. So they provide access to run stuff on GPUs, compile stuff for GPUs. If I do the same command on Zeus, module avail, it will take a while. And here you have a very different set of modules, but it is still ways of providing access to software. So, and libraries. So the example would be, let's say, for compilers, here's an example of a compiler, GCC. You could then load that module and get access to the GCC compiler, specifically version 8.3. And that is, oops, go on. That is what you see here, module load, module name. And you can even see with the default modules that are automatically loaded the second you log in. So if you log in a fresh thing, you'll see suddenly modules. There's the Pawsey tools. These are things like Pawsey account balance that allow you to look at your account and allocation. Slurm, which is a scheduler. It happens to have loaded a default GCC compiler and a specific architecture on Zeus. So there's different types of architecture on Zeus. If I do the same thing here, you'll see on Topaz, again, there's Pawsey tools and Slurm. There happens to be a GCC compiler loaded with a different version, but there's another module that specifies the essentially CPU architecture, and then here it happens to be a different one, Cascade Lake. So that module list command shows you what's available. So now if I do a module load, and I can just do something, we can just try module load Gromax, because you can see at the top of the screen there was Gromax, there was one listed, and now we can do module list. And you can suddenly see that there's a few different things that have changed, and that's because the module is meant to provide essentially access to not just the software, but if it depends on any other bits of software or libraries, it loads those modules as well. So this Gromax one has loaded Go and Singularity, a couple of different modules. And you might be confusing them. Well, what is an actual module? Well, we can go module what is, and we ask, let's say Slurm. This one doesn't have any information, so it's very useful to kind of see that sometimes something isn't set up. Here, module Go, principally because module Slurm is always loaded. You want to run through the scheduler. But here's an example where Go tells you, you can ask what the module is, and it says, well, it's providing an open source programming language, it's providing a compiler, and it was compiled with GCC 4.8. What about Gromax? Gromax edits the path to use the Gromax tool tag 222. So here, it's a simple, brief summary of what goes on. If you want to swap,
sorry, Pascal, you may want to use the show command as well.
Yeah, I will. So let's do module show, which is a little more informative, and this gives you a better insight to what is happening with a module. It sets some environment paths. So here it updates the executable path to include this directory so that you can then run executables. I think I can go to Zeus. I'll just see here. Well, we can just do module avail, and I can ask if there's a module Go, and and there's a module Go, and I can go, okay, what is here on Zeus? Oh, it looks like it's the same thing, and I can also do module show Go, and it will show what Go is actually setting. So Go is actually setting a bunch of different paths. These paths then provide access to the Go compiler. So I can now type to object query. I can even look at this particular path if people are interested and see what's there. So there's Go. There's that compiler there. So if I then, you notice here, if I do try to do Go and type it, nothing happens, right? It says that command is not found. But that's because I haven't loaded the module. Now I have access to this command. I can also unload this and then type the same command again. It's like, I don't know what that is anymore because it's unset that path to that executable. So you no longer have access to that particular bit of software or that library. The swap command, which is listed here at the bottom, one of the bottoms, swaps a loaded module with another, but the idea usually you're swapping between related modules. So I would do module, so if I do module list, I might go, oh, I've got GCC here. I go, oh, okay, well, I want a different GCC. So let's look at module avail and see if there are any GCCs. Oh, there's a few of them. Now, the idea here is the best practice is to swap GCC. And I can obviously be explicit, but I don't have to be because this is a current loaded GCC and I can go GCC and I want a specific one. And now you can see it's changed. So if I type GCC version 8.3, if I undo my swap, so let's go back. You can see now it's 4.85. So it's swapping. Typically, the idea of swap is you're swapping a module that's meant to provide the same type of functionality with another module that might be different. So then, you'll still have normally the same interface. So hopefully, that's the idea of the swap command is that you'll have the same command. So if we had two different versions of Go, the Golang compiler, you could swap different versions. And so have a play. You can see that. I will just quickly do this now. So if I do module load CUDA here and do module list, just something you notice there's a CUDA library, but that module is not available on Zeus. Oh no, it is. Sorry, it was a GPU cluster. It's not that useful anymore because it doesn't have any GPUs, but it did have GPUs before. But there's not equivalence of modules everywhere. So if you ran a bit of code on, let's say, Zeus with a bunch of module loads and have that translate, I think that it will translate immediately to Topaz, you may need to look to see if the same versions are available or even if the module is not available on Topaz, because the focus of the two clusters is slightly different. I will show Christian's got a question.
A quick question about what does D and LD between parentheses in the module list output refer to? So it basically refers to the modules that are loaded by default.
Oh yes, yes. So D is default and L is loaded. So if I go here, let's do CUDA, right? I've loaded CUDA, so it's loaded. There's the L, and it's the default one. So the idea would be, I would always suggest that you be explicit, but if I'll just do unload CUDA, let's do module avail, you can see it's now just got a D. If you don't type a version, that whichever one has the D, if there are multiple versions of the same module with different version tags though, right? It's the same CUDA, but different version tags, there'll be one that's default and you don't have to type the version, it will load that one. But my suggestion is to always be explicit and always be like, oh, I want definitely 11.1. I want to load. And then if I do module avail CUDA, you'll see that the L is now on 11.1, D is still on 10.1. Another question, yes?
I think a very important one. Is it possible to access a version of a module not in the list?
So if the module is not on the list, I mean, there's no module present, you will require that you can update the module path. So the module environment looks in specific paths for module files that then provide environment variables and everything else. But if it's not on the list, it does require either that you have your own version of that software or build a module that provides access to that software. I'll just do this here. Path, this environment variable that happens to be here, you can see it lists a bunch of directories. This is where the module environment on Topaz is going to search for module files. So I might go into opt module files, and you can see there's stuff in Slurm, and there's a bunch of different module files of Slurm. It'll look for modules in this directory. If a module is not present anywhere, it just means that we don't provide that. I mean, typically, if the module is not available, it would require that you either develop, port the software, compile the software on the computer for access for yourself in the group. And if you want, you can also produce your own module file. We have tools to do software install, like someone can put that into the chat. But if a module is not present, it's typically that we will assist, but we will not necessarily do it for you because the modules we provide are the ones that Pawsey supports. And going forward, it will be important to realize as well. So both Zeus and Topaz have compilers like GCC, Intel listed as compilers. So these are compilers: the Intel compiler, the GCC compiler. So if I do it here as well, avail GCC, so Intel. Oops, not module Intel, module avail Intel. You can see these compilers. I'm gonna, oh, sorry, I don't want to do it. I want to do it in my, okay. I'm gonna access Magnus, my own account, because I do want to show that there's a slight difference in Magnus. So if I do module avail GCC, there are GCC compilers on Magnus. This is the big supercomputer that we have. But the idea for Magnus and Cray environments is that you don't access compilers directly. So for people who are needing to build their own code or use specific libraries of the code, for Magnus, it's a different type of thing. You have a programming environment. So module show. We have these environments called programming environments, so PRG, ENV, and there's a few of them. So we can do module avail. I'll just do module avail because I'll show you where they are. There happens to be 3 different programming environments, 3 different types. There's Cray, GNU, and Intel. And this is how on Cray systems, you actually switch from different compilers. So you would actually not do program, let's say swap GCC with Intel. You would do programming environments on Magnus. You would do module swap programming environment Cray with programming environment Intel to access a different compiler and a different set of libraries. And that's what's listed in this table here. They have compiler modules, but they're not, they don't have the same naming convention or exactly the same structure as they do on Zeus and Topaz. So we've done some examples on Zeus, right? I suggest that you give this a try and see if you run into any issues of swapping the compilers, loading modules. And I would try both on Topaz and Zeus. And so I'll give a minute here. I'll wait for a minute or two so you guys can try the commands yourself. But feel free to ask questions while we let people have a go at trying the module commands.
I just wanted to add that the reason behind modules is because we install software in non-default locations because we want to have several versions of the same software. So you cannot install the software or the software under /user bin because then you can only have one version of each software. So we install in different locations, but the OS cannot find the software without hints. And modules provide a nice way to provide hints to the OS where to find the software.
Yeah. So I'll give a quick example as people are playing this. So if I do module load, I've already got CUDA. So if I see what CUDA can provide, right? So let's just do CUDA for now, right? It'll show me the path. I could then look at these paths and go, what is actually provided here? And so look in the binary directory and you'll be like, okay, this is the executables that I can run, that I get given access to, right? So you can see these naming conventions here, CUDA, memcheck, etc. If I module swap CUDA with, let's say, so now I have different versions. Is it 2? 4.2, there we are. So now I can do the same thing. I can, I'll just show again, so we can do module show CUDA. And there's a different directory now for where the executables live, right? It's now not 11.1, it's 11.4.2, but as Christian said, if you tried to have these, they would have to have different names. They're all the same name, but just a different path. And so it's just an easy way of quickly changing the paths in which you're looking for executables that have the same name. It makes it easier for you to swap, unload, and load, and not have to worry about trying to deal with very complicated names. So you don't have to necessarily remember if I wanted this NVCC versus accessing this NVCC, right? So now you can see different compiler names, right? So it's the same compiler, the version is slightly different here. I've got build CUDA 11.1. On top, I've got build CUDA 11.4. Instead of having to do all of this explicit path to an executable, you can just type NVCC and then just module swap CUDA. Oops. Yep, there we are. And suddenly it's much more manageable. So that's the reason behind this module setup. How are people doing with modules?
They were thinking that they can slap between the clusters on the same terminal. So
I've got 2 terminals open with a login, two different things. So I just happened to log in twice. I actually have 3 logins, right? To show you, I've logged in separately. One terminal in Magnus, another terminal is Topaz, and another terminal is Zeus. So I can swap between the different clusters to kind of emphasize differences. So here, in case you're wondering, so sinfo, right? You could specify a cluster name. It could be like Zeus, Magnus, right? And look at the Slurm, where Slurm can pull different clusters. That's not possible with module. Module is focused on one cluster. And so you can't view the modules that live on another cluster from, like on a remote cluster from your own different cluster. That's not possible. Okay, so I might move on, but I'm happy to kind of go back as we'll use modules continuously. So if you've missed a few things, don't worry. We're going to reinforce this as well because we'll use modules as we're going forward. So I have mentioned that there's slight differences on Magnus where you have these programming environments. These programming environments provide wrappers to all the compilers. So the C, C++ compilers all have the same name. Because on the Magnus, for people who are going to using Magnus, they have wrappers that kind of identify an alias something. So here I should show, so here I'll just do module list again. I have GCC here, so I have the GCC compiler, right? The GNU policy and C++ compiler that allows me to build codes from source and then execute them. Essentially, it provides the executables. If I then module swap GCC and type GCC, I still always have access to a system GCC. But now if I do Intel or ICC, I have access to the Intel compiler. And on Zeus and Topaz, these programs that would generate executables from source code have different names. So you go from CCC to ICC to build stuff. Whereas in Magnus, the C compiler is always is this wrapper. It's always called CC, no matter what actual real compiler using. It provides sort of a front end or an alias, if you will, to access compilers that are essentially Intel or Cray or GCC. And these are different ways of building the executables. There is also optimized libraries, as we mentioned. We do provide a set of optimized math libraries for building code. So there's like fast Fourier transforms or linear algebra through Cray FFT and Cray libsci. On Topaz, obviously, I did mention that Topaz is particular with having lots of CUDA, so lots of NVIDIA CUDA libraries that allow you to access and make use of GPUs. So you can see there are other exercises to kind of try available to see what HDF5 is and see what happens when you look at HDF5. So I'm going to do this on Zeus because it's kind of useful to see. And I can go module list just to see what I have. So I have this as my default HDF5. You saw it briefly as we go along. So HDF5, it's got paths. So here's this path, Pawsey, Sandy Bridge, Intel. I happen to be using the intercompiler, right? HDF5, something else. Now, if I swap back to GCC, and I show HDF5, suddenly that path is different. And it's because the module system has updated the fact that the path points to the compiler, and that's dynamic. So if you switch compilers, it will point, if that module is available for that compiler, it will automatically update the HDF5. So if I do which H5 dump, which is one of the HDF5 utilities. Oh, here we are. I don't know why it's not there. So let's module load again, HDF5. There you go. So you can see the paths updated, but I want to make sure that I really reloaded all the paths and reset stuff so that it's the first instance of H5 dump that's found. And now it's pointing to a different H5 dump. This command, right? So this command is now pointing to a different path, normally the same executable, but built with a different compiler. Okay. So I will briefly mention containers. I would love to go into this in more detail, but it's quite a complicated, well, it's not a complicated topic. It's just a topic that takes a while to go through. So containers, we've mentioned modules are the kind of way of providing access to software. And some people did ask, well, what happens if that module is not available? And one of the paths that we provide at Pawsey is the use of containers. So containers provide a standard unit of software that essentially takes a code and all the dependencies, all the libraries it has, and puts it in a little box that can be used to generate an instance of that software. And that's called a container, and it's reliable. It essentially provides a reproducible executable. It has operating system level virtualization, but the idea is that if particular packages module is not available, and I can think of a few where we do provide containers for. Example, Alexis, if you are ever running, if any of your projects are run OpenFOAM, the OpenFOAM modules we provide essentially are OpenFOAM containers. We don't necessarily provide the raw software itself. We provide OpenFOAM through containers to kind of encapsulate all the dependencies and make it a bit more manageable to use. And we run these containers with Singularity. So I mention this here because I know that some projects will have to make use of containers. And so just to emphasize that Pawsey does provide support. We've got documentation on containers, on container use, and how to make use of this software in this fashion. Okay, so that's the software access. You've now launching programs. You've already done one, right? So you've had Christian introduce you to essentially running the host name. So that's Slurm executable, which allows you to do a bash script, but you can also do stuff immediately. Run srun. It'll essentially put in a request for compute resources and then try running executable. So on Zeus, through our allocation, I can run srun. I could try to run SLS. And if I don't write anything, it's essentially a very naive 1 CPU, 1 core request to run a command ls, right? And so I could do hostname. So we can do this, Zeus1 srun. Now this depends on where this is running. So suddenly you see there's a change. Hostname running on login gave me back Zeus1, srun hostname gave me back a different hostname because it essentially got put on a compute node and run there. I can actually provide arguments to srun to put in lots of requests for resources. But you can see if I ask for help, srun can have a lot of extra arguments. So typically the advice is to not use srun because then you'd have to remember what you provided at the command line. And also that putting in a full resource request is a bit verbose. But you can, of course, do srun and ask for 1 node, 2 tasks, ls. It will then run on 1 node, but it will run essentially 2 tasks, and the task it's running is ls. And so it ran 2 versions of ls. I could run 28. I get 28 foos. That's the file that happens to be in my directory. If I do hostname, it's all the same hostname because I'm asking for 1 node. If I ask for all 5 nodes, which we have access to through our reservation, all of a sudden I'm running on a bunch of different nodes. And it's split up the 28 tasks as best as I can on 5 nodes. So you can see 86, 87, 88, 89, and 90. It's all running there. So this is a way of running parallel jobs. So if you had something that would be, software, you could put in whatever you want and it would run it in parallel. srun is a way of doing this. You can see the normal thing we have here, number of nodes, number of tasks. You can even put a request for GPUs. But these are the best approach is to do bash scripts. So in case anybody hasn't done it yet, my suggestion is that you grab the repository that we provided. Has anybody not grabbed this repository? If not, my suggestion is to put and if you've had difficulty, just put in the chat window and then someone can help you get through and grab the repository. Now, let's try running a single core job. So I kind of did that already, right, with ls. So list is essentially not a multi-threaded executable. It runs on a single core and it's completely serial, right? It doesn't try to do anything parallel. We can try running on Zeus and on Topaz single core jobs. I would point out that going forward, when you get access to Magnus, don't run single core jobs on Magnus because essentially you get access on Magnus. There's no shared resource on Magnus. So you get a node. If you run it with 1 core on that node, you're still given all 24 and you're charged for all 24 on Magnus, even if you run just with 1 core. Whereas on Zeus, it allows you to share nodes. You can put in a request for 1 core. It will give you access essentially to 1 core on 1 node, and someone else can get access to the same node but run on different cores. It's a shared resource. That's in part why we are running our training on Zeus, so you guys can all share resources. So there is a serial Python code in our repository. So we'll go to, I just saved it as something else. Zeus, this happens to be the repository. You can see hello serial. So if I go into hello serial, this directory contains a script. The one that we want to focus on is hello serial slurm. Quick thing you'll note that the reservation that is listed there is not the correct one for training right now. It's not course, it's interns queue. And this is requesting a single node, single core, single task, and running Python. It just happens to be running this hello serial Python code, which just prints something, right? You can submit this. My suggestion is you try submitting and then see what happens in terms of resource request. The code as well, you'll notice here, I am not doing the launch through srun. So if I look at this line here, launch, I've just got Python 3 hello serial. If I really want to make use of the compute resources available and make use of multi-threaded, et cetera, then you want to run srun Python serial. So let's, I will edit. People can edit it along. And we can run. Now it doesn't really matter for srun if it's serial code. It's serial code. But we can then submit this. Sorry, I've got that little window in front of me. I can then look at the queue. It's already run. There's a Slurm output. It's got hello world. So that is the resource request for running serial jobs. And remember that if you're running serial jobs, you really want to run on Zeus. Other systems are not really set up to be the best way of doing this. There's also suggestions of trying to not run serial jobs. So we've got different ways of collecting serial jobs like job arrays and multiprog. There's documentation on that. I'm happy to go through that idea, but the breakdown you've seen is a resource request, loading modules, and then running something. Okay, so MPI, so this is shared access. So if I then go to hello world, OpenMP, you can see now suddenly there's make files. So this is required to make the code. There's a source code. This happens to be the source code. It's a C program. It's a C program that makes use of OpenMP parallelism. There is a couple of Slurm scripts that you can look at where you have a resource request. You can see now task per node is still 1, right? So this is an MPI request, but we're not running an MPI code. So we still want essentially 1 MPI rank, but each MPI rank is going to spawn then 28 processes or OpenMP processes. And so you should get actually a multiple set of output as you go along. And if you change this request, then you'll see different numbers. So you can try playing with this particular code. Let's go Slurm. So here, I'm going to be explicit. I'm going to, by default, GCC is kind of loaded, but we should try to be explicit. So module load GCC, you could do swap to make sure you always have some particular GCC. We could want to make sure that we can run it. So we want to do interns. All of this OpenMP environment variables, you hopefully might touch on in some the later talks about parallel, like actual parallel programming. But you can see I'm running something, and I'm running this -n is just saying run on one node and run with this many cores. But if I actually take this away, srun will default to whatever the resource request is above. You won't have to necessarily specify it, but you can always specify if you're going to be explicit and you also want the imprint to be different. And here I can see what I've got listed, and I've got GCC, and let's do module, well, I can leave it there. And we can make, you're like, oh, didn't make code. So I don't know how many people are familiar with compiling code, because this does require compiling some code, but you can specify a file and it will now make the code. So now I have an executable, this hello GCC, and I could try running it on the login node, right? And suddenly you're like, oh, it runs on the login node. And it looks like it's running in parallel on the login node. And that's because there's shared parallelism. So shared memory, you can run in parallel on the login node. And at least this particular code is very lightweight, right? It's just printing something. But the idea is, of course, is to do this in srun. So you could be, I ran it on the login node. I could run this on an arbitrary node, and you'll notice something different. Suddenly, srun, I went from login node providing lots of parallelism, like I suddenly had lots of threads running, and then srun suddenly just one thread. That's because srun is defaulting to one thread. I then spent 5, I suddenly get 5 threads, and then I can always submit the script. GCC. I can look at the queue. It's running. It's finished. Is there a slurm output? There is a slurm output. The slurm output, by the way, is always typically, not always, but it's typically slurm dash and the job ID. So you can see I've got the job ID here when I looked at my queue. That's also the file, part of the file name. And that suddenly has exactly what happened when I was running, and suddenly there are 28 processes. 28 threads running in total, as you can see here, and each thread ran. And it ran on a compute node in this case, not the login node. I'm going to pause briefly here because I know that I've also introduced compiling codes and a new type of parallelism. Does anybody have any questions? I'm happy to wait.
So I guess there was a good question about about the file system and about being visible to our compute nodes. I think more in general, it's important to say that compute nodes in the same partition look the same.
Yes.
Because it makes it easier to program than to run jobs.
So a partition does not need to be homogeneous in terms of compute resources, but it's much easier to manage if they're homogeneous in terms of the resource request, in terms of nodes. If you had wildly varying nodes, it's much harder for you would also get maybe poor use of some nodes if they suddenly if one node had 66 threads and the other 66 cores and another had 22, Slim would know, but suddenly you would probably maybe access only 22 of the 66 because it's in the same partition. So it's much easier to manage if they're homogeneous.
Can I ask a question quickly?
Yep.
So just about like a keyboard shortcut, I think you're doing. Sometimes you're typing out like half of a file name and then looking like you're doing some sort of keyboard shortcut to show you all of the possible completions of what you've already written. So I know,
yes.
You know how you can like tab complete something?
Yes.
Yeah, but it looks like you're doing something else where it shows you like all the possible.
So if I do tab twice, so if there's a multiple set of possibilities.
Oh, right. If you tab twice, it keeps what you've written.
And it's just like, okay, well, everything that starts with mod is this that you have access to.
Right.
And then if it gets to the point where there's only one unique, it'll just complete. So module, there's nothing else that goes, tab completes.
Yeah, okay. And when you say threads, is that number of nodes?
No, so threads is essentially per core process. You can, it's a bit of a funny thing. So on a CPU, right, you have multiple cores, essentially multiple computing units.
Yeah.
Each computing unit effectively can run one thread at a time or one process at a time.
Right.
The terminology is usually a thread is and a process are not quite interchangeable, but very much mapping. Like you're running a particular set of instructions. And that would be one thread running a particular set of instructions.
Okay.
A node so the idea is that one is just about like running instructions. So how their instructions are run and how things are managed could be hardware specific, because you can run with many threads on a single physical computing unit. What happens is that one thread will take precedence, do its set of instructions, then another thread will come and go, well, now I can run my instructions. So you're kind of waiting. So I think briefly it was asked in the chat about a Slurm thing, which has processes per CPU. And typically you want to, I mentioned this as well, so it's a good question. You typically want to make sure that you have essentially one set of instructions to run per core, because the core can't handle multiple instructions fully. There is something called hyperthreading where you can run instructions that are purely logical instructions, like an AND or an OR. You can run two at once, because typically a lot of computing units have two logical essentially units in the computing infrastructure. They can run two logical instructions completely independently at the same time. But a floating point operation, there's only one per physical core, essentially. There's one floating point set of instructions you can kind of run. The threads are sort of a higher level there, set of instructions you want to run. And then nodes are an amalgamation of hardware. So you have a bunch of RAM and CPUs with maybe multiple cores, and that consists of a node.
Okay. All right. Thank you. So nodes don't necessarily contain multiple cores. Not
necessarily. If you had some very, very old supercomputers, right, that might have had one, like the first supercomputers would have had multiple nodes, but per node there would have been one CPU, and that CPU would have only had one core, right? If you go back way back in the day, some older computers.
Yeah.
Now they're essentially, if a CPU is provided, all the CPUs that are essentially constructed right now are all multi-core. They all have essentially multiple compute units. And nodes typically are dual sockets. So they usually have like two physical CPUs that have multiple cores that can do computing.
Right. Okay. Thank you.
Okay. So I'm happy to do the MPI example. And so I kind of did it as well. So let's go through the MPI example. So this is going to be across nodes. It's not going to be shared. You can do it on one node, but you can do it across nodes. So let's go hello MPI. Okay. So we can make. Let's do this on Topaz. So I'm just going to switch up because it'll. So I'll go into my Scratch. Same thing, right? Remember, I've got access to the same Scratch. Yes.
So while you do that, I'll answer a couple of questions on live. So the difference between SRAN and SPatch, because you use the SRAN to launch some application directly. So well, SPatch submits jobs for later execution. It puts the job in a queue, whereas SRAN waits for resources to be available to execute the job.
Yeah.
And so SRAN is used within batch scripts when the resources are already available, because the job at that point had already waited in the queue, for the resources. And when SRAN executes, it has the resources allocated. If you run SRAN on the login node, then I believe Pascal can confirm, but it would hang if resources are not available.
Yeah.
And the other question is, if we specify an impossible configuration, for example, CPUs per task, 1,000 or 100,000, it does not exist.
Yeah.
It would fail the job execution because it cannot be satisfied.
Oh, forgot. I need to go through this. So I'm just going to take this away. So let me show. So I'm gonna. Where? Oh, sorry. I need to add a. So I'm going to do the MPI example.
So sometimes the issue is that these examples have been written a couple of months ago, and we update software, and sometimes you need to update your scripts and you have to update your workflow because maybe the software that was used at the time was not available anymore. It's been removed because deprecated or something. So sometimes you need to brush up the scripts.
Yeah, so I'm going to be, so I'm in that request, right? So I'm running MPI. I'm asking for 1,000 MPI per node, right? So I want to run 1,000 MPI job, but Topaz.
I would actually be careful on the terminology. You would run tasks, MPI tasks. MPI jobs is different.
Yeah,
because
sure.
it's quite confusing using all these terms. And at this point, I would take the option to differentiate between process and tasks.
Yeah.
So I don't know if you want to do that, Pascal, or I can do that.
Well, so for MPI, for Slurm, It's very common to write task. There's lots of echo, Christian. Oh, no, it's gone. It's gone. So MPI tasks. So MPI is this message passing interface that essentially spawns effectively the executable a bunch of different times. So if you ask MPI run, I've got this example I can do because I've got MPI loaded. I can ask for 10 LSs. So I'm listing it 10 times. MPI, what it does is it will take that and go, I'm going to take 10 LS commands and run them. And for MPI code, what happens is usually that there's also communication between these instances that are running. So they can kind of communicate with each other. But each MPI task is given essentially an executable to run, and it will then run it. And if there's no communication between MPI tasks, like an embarrassingly parallel problem, you essentially get what I've got as this output, which is ls, which is not, ls is a command that's not parallel, it's not MPI aware, it's completely independent. So essentially it's as if you're doing ls 10 times and you get the results 10 times. If you're running commands that know about MPI, then you can get some communication between the MPI tasks. The MPI task can then start running different processes. So an MPI task can then go, okay, I've got, let's say, 7 different instructions to do. I can then spawn 7 different processes to run those instructions if they're independent or if they're dependent. And that is the difference in even in Slurm, it's replicated here. The term is old, it's kind of bad. So tasks is essentially MPI related. CPUs is not CPU related, it is CPU core related. So before this, the CPUs only had essentially one computing unit, one core. There was a direct mapping between the number of CPUs you're requesting and the number of cores you could run, like the number of supercomputing instructions you can run, processes you can run. But now that's not the case. So this is best, even though the terminology is stuck, it's not CPUs. You're not asking for a CPU, you're asking for a CPU core. And here, the terminology you can see in SBatch is very specific. I'm asking for one node. I'm asking for 100 MPI tasks, and each MPI task, I'm saying, I'm going to give you access to essentially one CPU core on which to run the instructions you're going to do. And I could change this where I could ask for 10 tasks per MPI. And then per MPI, I'm asking 100 MPI tasks. So and that means that I need, in terms of computing resources, 1,000 cores, right? So this would be a large request. Now, if I try running this, you can see bad job submission, more processor than permitted. I cannot actually request this type of thing because it's not available to me. And so at least on Topaz and Zeus, the footprints are different. If I then start going down and go, let's ask for one task, one MPI task, 10 CPUs per task. So this was kind of similar to the OpenMP request. And then do Slurm. You can see it's accepted. It will run. But what's interesting, hello MPI, no, I have to make I forgot to compile. Sorry. Okay, let's submit that again. Oh, sorry, that's a shortcut for me. Doesn't happen on this account. So now I've got this output, and you'll notice I asked for a lot of cores, but I only asked for one MPI task. So I only see one MPI rank running. So there's a 0 and 1. So the total number of MPI tasks running is 1, and it's rank 0 of 1. If I then change my request so that it's more in keeping with running MPI, so if I'm running a pure MPI task, I want to put my parallelism here and not in the CPUs per task. And we can go. And here suddenly you can see that there's parallelism happening. I can see that there are 10 MPI tasks that are running with the ranks from 0 to 9, and they're all just printing hello world. And so that's why you kind of need to know, to some extent, what parallelism is implemented in the software you're going to run, because the resource request will impact that, right? If you're running a shared memory program and you ask for a bunch of MPI tasks, you basically get that executable running 10 times without the parallelism that's really implied in the executable. So it's not effective. It's actually, you're kind of wasting resources. And if it's MPI and you're asking for lots of cores, but lots of cores per task being something and task being one, then you don't get the parallelism you're expecting. Okay, so, oops, all right. Yeah, so the other thing that to go through is GPUs. Now, the GPU request that we've gotten, the executable got, remember that the GPUs are only available on Topaz. So if you tried running this on Zeus and put in a request, there are no GPUs available. It will not accept this request. And so the GPU parallelism is a little harder to see. So if we go into the vector add directory, so this directory has two codes, as it were. You can see a CPU vector add. This is meant to do essentially all the compute on the CPU. And then there's the equivalent GPU code. And here, the compute is being done on the GPU. So essentially there's allocations for saying to the CPU, talk to the GPU. So you can see there's a lot more code involved here. There's these commands called CUDA check error, like CUDA malloc. It's essentially a way of talking the CPU, providing instructions to the GPU on how much memory to allocate, and what instructions to run, and how to talk back to each other. So you essentially have to have some method of in the code of talking between the two. So if you do any development, that will be involved. If I look at the script, here you can see the script is going to run on, it happens to run on Topaz. It's got a very specific request. Here it's got the GPU, essentially device request, asking for a GPU and only one of them, and then running. Now, if you run the CPU code and the GPU code, what you'll notice is a difference in the amount of time taken to do the compute, and not necessarily immediately obvious a big change in the output, because the output is meant to be just providing a quick calculation of essentially a vector add. The other thing as well is that you'll notice, I've put it here, right, that there's this loading of GPU enabled code. So you basically have to make sure that you load stuff with the -GPU if you're on Topaz. This will be important for anybody who's doing GPU stuff on Topaz to do any compute. So if you look at the script again, just look at the script, you can see an srun nvcc code. You actually have to compile on a compute node to make sure you have access to the GPUs you want. So if you compile on the login nodes of Topaz, they don't have a GPU in the, well, so some setups might have on login nodes some GPUs, but typically we do not. And also going forward in Cytonics, the login nodes will not have GPUs. So if you want to compile for a GPU, you basically compile on a compute node. So you actually do the compilation there. And you'll notice, like the previous things I was doing, I was just typing make in the login node, which is not what you want to do here. So that's why this script is there. And then we can even, let's just update the script, right? So we have this srun add. If you wanted to, you could also then run just a GCC for compilation of the GPU code or the CPU code. So you could do add CPU. And then run that code.
So I would suggest to increase maybe the number of elements in the to see the actual difference.
Small. But the idea here is that the codes are quite different, and so you have to compile differently. And also, it's not here, but remember that you'll need to add the reservation.
So actually, there is a question or a note. You can actually you can compile CUDA code on a login node without the GPU. Not in every case though. If you because if you use the CUDA drivers, those are not actually part of the CUDA installation. And they are only to be found on the compute nodes. So for some codes, you actually need to compile on the compute nodes. In general, as a general practice, we always suggest or recommend to compile codes on the compute nodes in any case. Also because you compile for the specific architecture you are running on. The login nodes may be different from the compute nodes.
Yeah, this is particularly true of Topaz, right? Because even though the NVLink is down, we do have two different types of GPUs in the Topaz partition. They're separate partitions, but on the Topaz cluster. So if you compile it for one and then try to run on the other, there's going to be differences in drivers, and it's going to be an issue. Did you want anything else, Christian?
Not really.
Okay,
that's good.
So we have the script. We can obviously submit this Smash script. So let's see if it'll actually work. Let's see here. Oops. Okay. Oh, did I type it incorrectly? It is vec-add. Oh, not vector add. Okay. So in my Slum script, at least you can see that the CPU code run, I mistyped the compilation for the GPU. Sorry, the CPU code. I'm just going to move it. I would prefer them to have the same naming convention. So vector. Okay, so I've submitted my script with SBatch. I can look to see if stuff is there. And at least currently, the common array. Oops. Did you have, I guess that's a leftover, is that?
Oh, probably it's a leftover. Yeah, there is probably, yeah, it's a leftover.
I might increase the size, as you say, because you might not notice it. So I'm going to increase the size of the compute. Make sure that they're kind of the same. Okay. I'm so used to it.
So what are you doing?
So I've just essentially updated the code to actually work. So there's some typos in the code. And I also just increased the size of the computing element that was being done. And I will just quickly show that on screen. So for people who are interested, I can do actually, probably be interesting here to see what's going on. So there's updates you need to do. So you'll need to change the script to have a reservation, make sure that reservation is there. Everything else is kind of fine. I've added a compilation to make sure that I've compiled the CPU bit. So the code would have worked, the script would have worked before, minus you need to add the reservation for interns. And that would have essentially produced a result, computed something, reported all good, and that would have been the end of it. And the reason I want to show AR63, let's do this. Print array, terse, implicit function array. Okay, so you still have some leftover stuff in.
I'll try to run the code because I copied this code from a folder I have. I'll try to fix this this one. So meanwhile, Pascal, there is an interesting question about about parallel programming and code. So does using CUDA or MPI directly can make the code parallel or run in parallel, or should we modify our code. So
Right. So just providing the, let's say, loading the module MPI and loading module CUDA does not provide parallelism. The code has to have in it the ability to use MPI and to use GPUs. Otherwise, just loading these, essentially the libraries and the compilers that are associated doesn't immediately provide parallelism. So you have to actually look at what the code is, what the code can do. For some people who might be doing some machine learning with TensorFlow and PyTorch, essentially those codes are set up to make use of those resources. So they will look for, but they're already set up. The code has been set up. If your code was set up like the Hello Serial Pi, right? Or even just a Hello Serial world, if it was a C code, you compiled it with MPI and CUDA. So you compiled with MVCC and MPI and everything. Even if you compile, use the compilers that are meant to provide the ability to access parallelism, if there's no parallelism in the code is still serial. It will not use those extra resources. You're just providing the ability to do stuff. So a good example, sorry, I need to exit that. So let's just go back to, is that code CPU vector add? So this is a C code. There's a couple of function calls to init a vector and then add some vectors. And if you look at the vector add, right, it's taking a couple of arrays and just adding it and saving it into another array. So that's the computation that's going on. Now this computation could be parallelized by MPI, OpenMP, and GPU. But as it stands right now, even if you added the ability to do it, the code will not make use of that because it's set up to be only serial. It will not make use of any extra parallelism. If we then go to the GPU code to look at what is necessary, you can see that the code has changed quite drastically. There's a vector add. This is meant to be a kernel run on the GPU that provides specific access to some bits of memory, and there's implied parallelism, or parallelism when you're actually doing the compute. So there is this vector add command here. This is essentially providing the parallelism to run an instruction on the GPU. And that GPU has inherent parallelism because it's got lots of computing units. And so suddenly it will do lots of compute in parallel. But you can see that the code change is not that, is actually, rather, it's not complex, but there's lots of things to do to make use of that parallelism. It doesn't suddenly just appear if you load modules.
Yeah, if they're trying to use some other softwares, they should look into the manuals and find out whether the software they
yeah, you should definitely look at, like, for the example when I was loading a few stuff. So there's module avail. We provide some software, right? So there's software that exists through modules. Some of this software is serial, some of the software is non-serial. So I'm just going to show this up here because it's kind of useful. There's even explicitly what's going on. So here, HCF5, there's a module that says, I'm providing you a library called HCF5, and it happens to use parallelism. There's one that is specifically non-parallel. That library has been compiled, and the code has been set up to make use of parallelism or to turn it off. So one case we turned it on, in one case we turned it off. But you need to look at what software you need to use. So Forge, actually probably FFT, is a good example where you can run this fast Fourier transform library in parallel, in serial mode, in parallel mode. Which one's which. I mean, here we provide all, but you need to look at the software that you can use. They should tell you, the read the docs documentation should provide information of how it's running. Okay, so have people played with running a job and looking at output? If you haven't and you're struggling, can you please let us know? Any comments? Okay. So we have gone through non-interactive parallelism. Essentially, like you submit a job, it waits for resources and it runs. Yes, Christian?
So there is a question regarding the SLAM file for the GPU.
Yeah.
Does CPUs per task specify CPU cores or GPU cores?
So the request, let's load this up here.
So essentially, once you request a GPU with the GRES GPU, you request the entire GPU. There is no partitioning of the GPU like there is a partitioning for the CPU, let's say.
Yeah. It is not possible, or it's very non-trivial to try to share compute of a GPU. So you ask for a GPU, you get all of it. If you use one of it, you've gotten access to all of it. It will just run one instruction. So the good example would be, you'll notice the lack of, let's say, speed up of using a GPU. It'll probably be even slower. If you don't use, if your compute uses, like if it did just one add, doing one add on a CPU is much faster than sending the scalars to the GPU, using one portion of the GPU to do one add and then sending it back. So you get all of it. And in terms of all the SBash commands that relate to number of tasks, number of processes, number of threads per, or CPUs per task, and number of tasks per node, that all relates to CPUs. The GPU request obviously is for the total number of GPUs. So you can ask for more than one GPU. We could do 2.
One important thing that we mentioned here, that GPUs are tied up to the host CPUs.
Yeah.
That's how you reach the GPU through CPU.
Yeah. So you always need to have some CPUs to talk to a GPU, right? And you can see I asked for 2 GPUs and it ran, the job went. But if I then asked for, I don't know, let's ask for 784 GPUs. No, right? There's only 2 per node. And those 2 GPUs, essentially we could try to enable this, but it would be very slow to have GPUs talk to a CPU that exists on a different node, in terms of, because ideally you want the CPUs that do the most talking to a GPU to be on the same node, on the same motherboard, and you minimize memory communication. You can, of course, do communication across GPUs, across nodes, and across CPU communication across nodes with MPI. But for really fast access to a GPU and memory transfer, you hope the CPU that does the most talking to a GPU is the one that lives closest beside it in memory. Okay, so we can do some interactive allocations as well. So we've done all the stuff. So I want to, I guess, maybe show this. So srun 5 or 5. I guess it'll run immediately. Let's try 28. Oh, I didn't make it. Sorry, I ran this on top of this. Let me just make. Oh. Module loading the OpenMPI to make the code, because this is an MPI code, so I need to have access to that module to then compile it. So I've got that code. I've got an executable. I can then run that executable. So let's actually edit the script. It's Slurm, right? And now let me run with 5 nodes. And I'm gonna take this away because I want srun to just follow the full resource request that's in SBatch. Right, so you've seen this type of thing where SBatch, I run then, so Slurm. What did I do? 5 nodes. Oh, did we get 4? Oh, sorry, 5 interns. So I'm updating the reservation. And I just want to reiterate this to show, okay, so I put in a request. It's then going to run. Sorry, I always have a shortcut that usually I do. it's now running, right? It's running in the background. It will finish at some point. It finishes. I can then look at the output. There's 140 things running at the same time. I can then run srun and put in a similar request by going 5 nodes, 28 tasks, reservation equals interns queue, and the code I want to run is the hello MPI. Help if I can type. And you can see now this is sitting for a little bit. It sat, that srun sat for a brief moment to try to make sure it could get resources, got resources, and then ran. So if we all do this command, if everybody put in this command at the exact same time, you'd notice you'd wait because someone would get access first. Everybody else would have to wait for that code to run, then get access, and run, and so on. Right? There's not an immediate request. I could then, but I don't get to interact with that output, right? I want to interact with something. This is where this command, salloc, allows you to essentially get access and interact with something. So if you were debugging and you were really interested in debugging code or looking at how things behave, salloc is a nice way of doing this. So we can do, let's do 2 nodes. Let's do 2 tasks per node. So this is salloc. Obviously, you're going to have the reservation that I want to use. And then you can see I'm waiting to get those resources. I suddenly have resources, and suddenly I'm back to command prompt. So you can see the difference though, right? So our login node was here. There's Zeus1, and suddenly I'm on Z043. And it's because I've asked for an allocation, an interactive one, on the compute resources. So now I'm running interactively on the command line with compute resources. So now I can do make, it's already made. I can run hello world. It's not going to work super well because it's waiting for some MPI, but I can do srun. And now I don't have to, it'll just run automatically. And you'll notice there's only 2, but it's because I'm running on 2 different nodes. So if I do host name, you'll see 2 different host names pop up because I've asked for 2 different nodes, and I've asked for essentially 2 MPI tasks. That happens to be 1 MPI task per node. And suddenly I get 2 different nodes. I'm running actually on 2 physical different nodes, this command, right? And I can run stuff interactively. I can interact and I could say, oh, this is not what I want. Let's change hello MPI. I wanted to write, I don't like hello world. I want to say, hello everyone. That's the thing I want to do. I could then type make, and then I could run the same thing again. Oops, sorry. And suddenly I have hello everyone. So salloc provides an interactive means, and it's pretty useful for debugging. If you're debugging and you're kind of going to constantly edit code or constantly do some editing to get somewhere that you're happy with, to then send off a resource request that's larger, this is a very useful thing to use. The command is salloc. And then you, like srun, salloc provide the resources you want, the time you want it for, etc. So I would suggest everybody try an salloc command and see what you can do as well. So you could try running here srun. They've got an example, interactive sessions running Python serial. You can run a few different commands. The idea is that you'll notice that you'll be given a node. And some people might be even given, if everybody asked for, let's say, everybody try salloc 2 nodes, 2 tasks, MPI tasks. So this specific command, some of you will be on the same host. But if you looked at the cores you were given access to, some will have different cores. So I'll ask again, I'll see where I am. And can someone type srun hostname? I've been given 43 and 44 again. Is anybody else given 43 and 44? If you have, Joe, okay, cool. Now, so Joe is on there, and I could try updating my request. Yeah, go ahead.
While you were explaining that, I was fixing the GPU code. Actually, I had taken that code out of a repository, but there were dependencies missing. Sorry, Pascal. I've actually been running the code, and I wanted to show the results to the intern people, and I want to quickly share my screen.
Okay, go for it. You should be able to steal my screen.
Yes. Simply what I want to show is that. Okay. Many windows open. So you should be able to see my terminal. So I'm on an interactive session on a compute node with the GPUs. And at this point, what I did is, well, first of all, now that you are in interactive session, you can run your compilation commands directly on the terminal, or you can run your programs on the terminal, or you can simply run the same script without submitting it to batch, because at that point, those comments are just comments. And what I did essentially is the same code that Pascal showed, just that with all dependencies there, so it works. And what I did is I just left the commands to compile the code, and compiled the code already. And then what I did is increasing the problem size a bit to 1 billion elements. So we are adding 2 vectors of 1 billion elements. What I did is first running the GPU command, and I've run it through the profiler as well, so that we can take the exact time of the actual addition, because the code itself will also initialize the vectors, and we also do some clean up afterwards. Well, what we're really interested in is the actual operation of adding elements. And as you can see, this using the profiler is the fastest way for me to show you the actual execution time of the addition itself. And we have only one call to the function, and it runs in 14 milliseconds. So if then what I did is timing the CPU version. Now the CPU version, there is not a the quickest way for me was using the time command. The time command reports 24 seconds. Now, if you consider that there is also the initialization of the 2 vectors, you can, how to say, for simplicity, you can even divide the time in 3, evenly between the 2 initialization of the A and B vectors. And then there is the addition. And even if you divide by 3, then you would get something around 8 seconds. But you have 8 seconds compared to 14 milliseconds. So it's actually a couple of orders magnitude faster the GPU.
Yeah.
And as you can see, once you request during the allocation itself, when I request the interactive allocation, I ask a GPU here. Then when I run my command here, the command is able to see the GPU without any particular command. But this is to be used for this kind of profiling and interactive sessions. Usually you write the script to run your program.
Okay. Do you want to stop sharing?
Yes.
Share? Okay. Okay, so the people have tried interactive sessions, I hope, and feel like they're comfortable a little bit to explore in interactive sessions. Christian showed you a very good use of an interactive session where kind of looking at debugging and profiling codes. So it's quite a useful thing to do. And even in our example, we also make a point of kind of like a lot of times people ask for the debugging queue. So the debugging queue and the GPU debugging queue, these are partitions where you can only request minimal resources, but you're given quick access to those resources so that it's easy to kind of get access. Now, real world use. So we've shown hello worlds of vector add, hello world MPI, hello world OpenMP, and kind of serial. They are normally quite simple examples. That usually the real world is much more complex. You have to do a lot more complicated instructions. But of course, you want to run whatever you're doing as fast as possible. And you want to minimize the wall time within reason to do some compute. So obviously, if you can run something in 14 milliseconds, that's fantastic. In the profile that Kristen showed, they also showed how the mem copy, so copying from the CPU to the GPU, and that was about 7 seconds. And so if your compute on the CPU only took 4 seconds, right? Even though the compute on the GPU took 14 milliseconds, you might be like, well, overall, I still wanted to use the CPU because it was the mem copy was long enough that I didn't want to do it. It was longer and so on. So there's things to think about as you're going along. So you want to eliminate the wall time, but you also need to think about the cost. So you cannot indefinitely scale code, right? At a certain point, adding another computing element, the example would be, Kristen went to 1 billion, we said, elements. So if you do 2,000 elements, you don't get a lot. If you do 5 elements, you're just not getting any speed up. The GPU is not providing any speed up. It won't scale any faster than doing 1, 10, etc. You really need a large number of elements to notice speed up differences. And there's also a certain point at which you will no longer scale. So if you're doing 1 trillion elements, one, you wouldn't be able to fit it on the GPU memory. But also there's memory bottlenecks. It's also how the code does stuff is like random access order. So if things are randomly accessed all the time, that can be quite inefficient. And so there's only a certain amount of how you can scale. So you do need to think about the costs for the stuff that you guys are going to submit. And it's the wall time times resources. So if you are requesting lots of resources to shrink the wall time, great. But at a certain point, the efficiency of the code will mean that you can't just keep requesting more and more resources. So and for large jobs, right, you might request it for 100 nodes. That's a lot of compute, and it ends up being about 28,000 core hours for one on Magnus. So if you're requesting that, you're using 20,000, 30,000 SUs or service units, and the typical intern program was 10,000, right? As a 50,000 on. Exactly. Okay. So on Topaz, if you got 20,000 and the thing you want to try to do took 30, kind of fine, but you're using all your resource in one go. So it might be that, especially if the code is very inefficient at that point, you could regress fewer resources, wait a little longer, and make better use of the allocation you have. Now, I kind of mentioned this as well, but you do need to think of how the codes are doing their parallelism, right? Whether it's distributed memory or shared memory, and just providing the presence of, let's say, the OpenMPI module. So provide MPI as a module does not mean that you get that parallelism. You have to make, that code has to be able to use that type of parallelism to begin with. Some codes are, best tackled with GPUs. Some codes are best tackled with CPUs. And then, some are embarrassingly parallel. So there's no communication. You're essentially doing let's say that LS that I ran. LS is an embarrassingly parallel program, hitting the server. But if you did something similar where there's no communication required, everything is completely independent, those real world uses that embarrassingly parallel problem can scale indefinitely because there's no communication required other than the initial start point, right? Now, in terms of HPC, as we mentioned in the first instance, the idea of supercomputing systems is that you have a computing unit that provides essentially a motherboard with CPUs, GPUs, high bandwidth like memory, and quick access between all these various elements on a given node, and slightly slower access across nodes. So the fastest thing is in terms of communicating memory. You're always going to do that. If you're computing something somewhere and then saving it, it's got to go to RAM. So it goes from the RAM to the CPU's cache, then goes back to RAM, etc. That's all on a compute node that's very fast. You then connect these up with very fast interconnect, but there are limitations, right? And there's even limitations. You might say, well, why not just build a RAM chip that's physically larger and has 2 terabytes of memory rather than a bunch of individual RAMs that contain 16 gigs and another 16 gigs, another 16 gigs. Obviously, if you need to replace an element, suddenly you're replacing 2 terabytes versus 16 gigs. So there's just obviously engineering issues, heating issues, and so on. So there's limitations to how much computing you can put with the fastest access in terms of per node. And also there's also issues of communicating across node. You can't have indefinite, 20,000 node computing superclusters because there's cabling and communication latency and so on. So the key thing, of course, to get across is the HPUs are not a simple large CPU or a super fast CPU. There are many CPUs connected together to do compute. So the software has to account for this to do it. And that's where OpenMP, MPI, CUDA comes in, and you have to have these codes that do it. But I wanted to raise this because it's kind of an interesting thing. So we mentioned at the beginning of the introduction, there's a computer called Fugaku that is on the top. It's the fastest computer in terms of the number of floating point operations it can do per second. And it kind of gets close to 1 million teraflops or a billion flops. So that's the gigaflops, right? So because it's close to the exaflop scale, but it's designed to has a fast interconnect and so on. But some programs don't really need that. So folding at home is a good example of an embarrassingly parallel problem. They send off little packets of data on your laptop and you do some compute. And the folding at home, this was a little while ago, but if you looked at what they got available to them as computing resources, they had 3 million CPUs, 250,000 GPUs, and or close to 300,000 GPUs, both AMD and CPU. And the total number of CPU cores, not just CPUs, but like computing elements, was 21 million, right? But it's an embarrassing of a parallel problem. So they were just running on laptops everywhere, right? They didn't need to do the fast communication. So this was exascale level in one software, but it's an embarrassingly parallel software. And that is a very special case. Most of the time we will not have, you'll need to have things talk to each other fast. And an example of protein, so protein folding at home is folding proteins, but like very simple calculations. If you want to do really complicated molecular dynamics, you could do something like NWChem, which is a software, and that does need fast communication. It doesn't scale indefinitely. At some point, given a problem size, adding more compute does not do anything. And so because each core is doing a bit of the simulation volume and then has to communicate the results often and quickly to other cores doing other portions of that simulation problem. So here's a good example of indefinite, so it's sort of inefficiencies that crop in. So here is doing a specific simulation with NWChem and the number of cores that they're adding into the compute to do it, right? So they're doubling every single time, and then the wall time, the decrease in the wall time taken to get results. And then here an example where you increase the computing resources by 2 and you kind of get a wall time shrinkage of 2. But then if you do it again, it doesn't shrink by half. You know, you are getting stuff that's running in less time, right? So here you're looking at 1 hour of compute using 1,000 cores, but then you're getting to, you know, still 0.75 hours of compute and using 4,000 cores. And so it's faster, but it's got much higher cost. So it's not suited to the resources you're providing. And so going forward, you guys will have to get used to the idea of thinking, what do I need to do? Okay, I want to do it in 1 second. Can I? Maybe not. You might have to wait 5 hours. And the 5-hour compute time might be not as good as just waiting 7 hours and using less resources. And you can't just keep pushing the number of cores, right? So there's this turnaround in which you get the relative cost of doing compute. So this is the cost as you increase the number of cores, the relative wall time. So it's dropping nicely. But at a certain point, the inefficiencies of how the computation needs to be done by the software, it means that throwing more resources at it means it's not an efficient use of those resources. And so the efficiency starts, the cost starts increasing. But of course, the idea is to try to increase the scope of your science. So we do want to provide resources. I have a question.
So can you get an estimate of the work time through experiments runs, essentially?
Yeah, so I will, how to explore. So I'll jump to this right now. So obviously it's very problem dependent, and it's not even code dependent. Some codes like the NWChem that I mentioned, some type of simulation volumes will be very efficient in how you can distribute workloads. And so you can throw more resources at it. Other ones are not. And so because it's a priori not obvious what the best decomposition would be, resources and wall time, you do have to experiment. So there are people doing scaling tests. Thankfully, for a lot of software that's available, like NWChem, other people have done scaling tests. So you can look at the scaling test and how the code behaves and go, all right, this simulation that they're running is similar to my simulation. It took 17 hours on 1,000 cores. It's probably going to be something similar. But realistically, if you are starting from scratch, not necessarily knowing how stuff scales, and you're kind of going from your desktop, I would use your desktop on small sample problems, see how it scales as you increase the problem complexity. And then when you're migrating to Magnus, Topaz, Zeus, you'll have to do the same type of scaling test where you have a fixed problem size and you throw more resources at it as you gradually increase, let's say, the number of MPI tasks that you provide to the code, right? It's really good to get the idea of the scaling tests. The wall time compute, like the total wall time taken something, is very non-trivial. It depends on how far evolved you want to evolve the system. So if you want to do a protein and fold it only once, figure out some folding, maybe that's not that bad. But if you want to see the interaction of a protein with other proteins over 10 nanoseconds, that might take a lot of compute depending on the interactions, and it might take a lot of time. I'd love to provide a more simple arithmetic, like mathematical way of determining the wall time required. The best thing is to start off with 24 because that's the maximum you can have, and also to make sure if your code has checkpoints and restarting. So the idea is that there's a lot of codes, as Basha mentioned before, which can run part of the way. So let's say you want to do 10 nanoseconds, and in 24 hours, you can only get to 5 nanoseconds. Some codes offer the ability to essentially go, I'm stopping in an hour, I'm at 23 hours, I'm running for 23 hours, I need to start writing an output so I can restart myself from this save point. So save the output, and then restart again. So that's why the suggestion is ask for the maximum time and see how far you get. Hopefully it's less than 24 hours. If it's more than 24 hours, and this was a question, if it's a lot more than 24 hours and you have checkpoints, so like restarting capability, saving capability, that's fine. But if it's not, that's a serious issue. And it's not a serious issue supercomputing wise, it's a serious issue of getting results wise, because if you need to run for 17 days to get an answer, what if this computer goes down in those 17 days, right? That is not ideal. So hopefully at that point, if it's the 70-day end result time, you can add more resources and shrink that 17 days down to 24 hours or less. And if that is not possible, that does require like thinking about what you're going to do, because it's not trivial now. That's a very, you have to figure out how to do stuff in steps. But always sending with GPUs, when migrating to GPUs, it's a little bit more complicated because it's not obvious to translate a task from a GPU to from a CPU to GPU. But I'm going to briefly mention that we can explore this if we have a little bit of time. I'm happy to do breakout rooms, but we do have a way of showing how GPUs could be used to speed up compute. We showed the vector addition, but a common thing is TensorFlow and some AI software. TensorFlow is a great example of software that is GPU aware. And so we'll use GPUs if it's available, and we'll severely reduce the compute time necessary. But again, how to explore in terms of how much you can scale, whether one GPU or two GPU, that's a trickier issue. Again, wall times, starting off with a simple set, understanding how much time it takes to do the simplest basic compute, possibly not on even the supercomputing resources, but then looking at how, as you increase complexity and increase resources, how that behaves. Of course, we are here to help, and as are the mentors who have had some experience using the Pawsey systems, but there's obviously tons of stuff on the Pawsey website in terms of documentation, good knowledge base. There's also support tickets. You can raise their request. If you are going to contact the help desk at Pawsey, it's really informative for us to know like everything about the job, like what modules you use, the error messages, job ID, etc. In all of these things, again, you'll notice the last statement, please never tell us your password. We don't need to ever need to know it. We just need to know every other detail of the job you ran. And there is occasionally Ask Me Anythings, which might be relevant in some cases. Yes.
Sorry, just one quick point. If you are contacting the help desk, put interns,
Yes.
intern in your message title so we know it's coming from you as an intern.
Yeah, so there's different ways of getting assistance. We even have Ask Me Anythings that occasionally show up. Usually they're themed. So maybe while you're an intern, there'll be one that's very appropriate for the type of work you're doing. You can join in and have a conversation. And that's the end of the second half of the training. I hope that was informative.